what's up, cuties? I am Bins. Don't you just love this sound effect? There's something satisfying about it, I feel like. I guess it's just me then. Anyway, this is a new episode in the Shapez BEASTMAM series, so welcome. Last time, I took you on a journey through the entire decoder, and I, for one, am still feeling the afterjoy. Call me a romantic. Anyway, let's zoom out and recap what we've seen. Or look at the layout of this decoder again. So the input signal that comes from the hub, it comes all the way from the right, and then it will move into the top left. Over here in the top left corner, we have our shape stability type checker here, which is going to decide which values we load into the side input of the clocks. Then we have our 5 parallel clocks right here. They are going to feed their output over here in the bottom left section of this decoder, let's say. And it looks like my screen froze. There we go. So here we have our combination module that is going to sort the floating pieces based on their lowest quadrant or their base layer, and then it's going to combine them to create those combo floats we talked about. From that, we are going to calculate the remainder with this subtraction module. Right next to it, we have the validator module, and then finally, last episode, we looked at the capture mechanism, which is located right here. And then today, what I would like to have a look at with you is this general area of the decoder, which is in charge of manipulating our shape signal somewhat and making sure that the physical factories, have everything they need in order to do what they were designed to do. So this topic of preparation is something that we will handle in 2 parts, and therefore today, chapter 4E, the decoder cap and prep, episode 2A, final preparations, part 1. The first thing I would like to have a look at is this. Remember when I said there were 9 smelt type codes? Well, I kinda lied. There is this extra one I decided to add for situations where the target shape doesn't even have any floating layers, because in that case, it just feels like a huge waste of time and energy to boot up the entire decoder and let it cycle. If a shape doesn't have any floating quadrants, then it doesn't make sense to artificially start extracting floating pieces within it and start cycling through them, right? Stable shapes can just be unstacked into layers and be output straight onto the remainder output lines. No questions asked. So let's take a shape that doesn't have any floating layers. I have one right here. And this one, right? And then we're going to go back. Oh, let's try that again. Let's cut the line. Now pause the game. Connect it again. And go back to where we came from. Excuse me. There we go. All right. Now, what I would like to do is wait until we get a signal right here. All right. There we go. So checking for for stability or for floating pieces in the entire shape is actually very easy. The only thing you need to do is you unstack the shape, you restack it, and you compare the output to the input. If they are the same, then you are dealing with a stable piece, and if they are not the same, then it means that during the process of unstacking and restacking, something must have collapsed. Your floating layers have collapsed, resulting in a situation where your output after stacking again will no longer be the same as the input. And that's a very easy way to check for stability across your entire shape. And that's exactly what I do here. So the shape gets unstacked, it gets restacked, and then you see that in this case, because we are dealing with a stable shape, this comparing unit will output a 1. In the meantime, this signal has also moved up here. This is another unstacker, an unstacker module with layer correction. And if we get a 1 on this line, then simply these 4 outputs will be sent onto the remainder lines, so 1 per layer. And simultaneously, it will also emit this 10th code shape that is also connected to the same NOT gate that we spoke about, with the only difference being that our shape signal, the one that tells the machine we found a solution, it comes from the right rather than the left, where the memory cells are. That's what we spoke about last time. But it will trigger this NOT gate all the same, which will shut down the entire cycler. So in this case, the cycler will be shut down before it even boots up. And that is because, this is a very quick module that is way faster than the actual clocks and the cyclers and whatnot. And it will shut down the cycler before it even starts by outputting this alternative code shape symbol that in this case I use for telling the machine that a solution has been found. All right. And then all of those wires, well, they just get all of those signals, they just get output and they get forwarded to the physical factory. And then the next thing I wanted to have a look at is this vertical thingamajig right next to it. So if we have a look at which lines come from the capturing module, then 5 of them, the 5 bottom ones, they will contain the float pieces that come from the clock, right? As a matter of fact, let me put in this second shape that I put here. So there we go. Then we go back, and then I'm going to also let the machine find a solution first. There we go. So we have these 5 lines, these 5 bottom lines. Those are the ones we're going to focus on. Those are the 5 pieces that come from the clock. And chances are given, well, actually they're fairly high, that there will be overlap, or in other words, duplicates. And we can see this in the example we have going on right now. So we have this one, and then this one's the same. This one's also the same. This one's also the same. And then finally, this one's different. So we have 3 duplicates, or we have 4 out of 5 signals that are identical to one another. So now on the physical layer, zoom out, let's go to the physical layer. On the physical layer, I have 5 floating piece modules in accordance to those 5 lines that come out of the clock. One little factory for every clock. And on the physical layer, it felt like a waste to put all 5 floating piece factories to work if 2, 3, 4, or even all 5 of them would be producing the same piece, right? Now, in theory, it wouldn't matter because those duplicates would be reduced down to 1 either way with how I set up the machine. We will get to that later. But I was concerned about speed. On paper, it wouldn't take much longer to produce the final shape if we produced duplicate floating base pieces. But in practice, I felt like the more machines need to run, the more that is going to affect the frame rate. And that, in the end, would mean a slower machine after all, because if you have 5 out of 5 machines running, then you have the machine, then you have the CPU calculating all of these shapes, and they run into the units and whatnot. So I thought, I wanted to reduce that as much as possible. And I have to admit that I haven't actually tested that hypothesis, but just to be on the safe side, I decided to add a duplicate checker on my wiring. And that is what this little thing right here is going to do. So if we end up capturing identical floating pieces, which as mentioned happens quite a lot actually, then I decided I will chuck those out and just keep the unique ones. That way we only boot up the minimum required amount of floating piece factories on the the physical layer later. So this module, it's actually super simple. It's a brute force kind of module that has 5 branching lines right here. So 1, 2, 3, 4, 5, right? They go up, and then I'm just going to compare them one after the other. So this is the piece that comes from the first clock, and it gets compared to the one coming from the second clock. And if those pieces are the same, then the second one will be shut down, right? It's as simple as that. It will be shut down thanks to this transistor here. So moving from the bottom upwards, we are going to compare the pieces 1 and 2, 1 and 3, 1 and 4, 1 and 5, right? And you can see we have a duplicate, 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 so we can chug out all of those lines. The next comparisons are 2 and 3, 2 and 4, and why don't we have 2 and 5? Why don't we have 2 and 5? Oh, 3 and 5, 3 and 4, and then 3 and 5 again. Oh, that's the problem. That's the problem. This is what we needed to do, right? See, I still make mistakes, even if my machine works. So, once again, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and 5, and now 3 and 4, 3 and 5, and finally 4 and 5. That's the complete set, right? So that way I am just going to remove all of these duplicates, and as you have been able to deduce, meanwhile, in this concrete case, since we have 4 identical wires, only one of those values is going to be allowed to pass, and that will mean that out of our 5 machines on the physical layer, only one of them will start producing this actual piece. Let's see, which one is it? In this case, it's the top one. Yeah, see that right here. So this is the one, and we had 2 of them, didn't we? Yeah, this is the other one. Okay, so only 2 out of 5 machines start running. That's the bottom line. All right, so that covers 2 module types that succeeded the capturing mechanism, but precede the physical factory. And I actually think, as a matter of fact, I would like to call that a wrap for today. Maybe this was a bit of a shorter video than the other ones, but at least we're making steady progress, and we are making sure that we leave no single stone unturned in this story. So once again, I want to thank you very much for watching. I hope you're excited to find out what's coming, and then I would love to see you again then and there. I've been Bins, thanks again, and take care. Bye.